Hello everyone, my name is Misael Romero Reyes. I am a current fifth year and I am part of the DNA subgroup where we use DNA for various purposes. In my case, I use it for purifying water and I do this using aptamers. Aptamers are these amazing biological molecules that when they come in presence with a target, they bind to it really tightly using non-covalent forces. They have various advantages like they're stable to harsh conditions and they're transportable at room temp, which makes them great candidates for use in other applications. One of the best things is that they're reversibly denatured. This means that by a change of pH or temperature, the molecule can be released and it can regain its activity by regaining its secondary structure so that this process can happen over and over again. Furthermore, there is a well-established selection method. This means that think about any molecule, then we can create an aptamer for that. In fact, there are people in our lab who do this and create aptamers for different molecules there's not an aptamer for. But in my case, I use it for an application-driven process, in this case, water purification. And for this, I take into account the use of membranes. Membranes have been used extensively for water purification, but the drawback is that depending on the pore size, the more expensive it is to purify the water. So imagine reverse osmosis, where the pores are really tiny. The amount of money needed to purify water is way higher than the one with bigger pores. So we want to get a great balance of this, and we use ultrafiltration membranes that the pores are big enough to remove bacteria, viruses, and big contaminants. And then our idea is to attach aptamers to it so that they can take care of the small molecules. This way we can purify water in a cheaper and faster way. And my whole PhD has been developing this proof of concept of attachment of aptamers to the membranes. So I'm gonna walk you through how I do that. I start with a hydrophobic polymer, in this case PES, and then by phase inversion process, I am able to transform it into a membrane. This membrane then goes radical initiation with AIBN and using methacrylic acid as the monomer to create this membrane with polymethacrylic acid chains. The best thing about this is that we have a lot of carboxylic acids, and this create a great platform for an amino-modified aptamer to come and attach to it and form a peptide bond or an amide bond and covalently attach to the membrane. Now that we have our membrane, we are able to check if small molecules are being depleted or not. So basically, what I try to do is to check if it's able to remove a small molecule. First, we're able to check by the change in concentration if the aptamer is attached or not. So by this change, we're able to see that DNA is indeed attached to the membrane. Then it's time to check if it actually removes small molecules. My contaminant of interest is bisphenol A, because it's often found in rivers, lakes, and reservoirs at a concentration of 200 nanomolar, but greater than 89 nanomolar is unsafe according to EPA guidelines, and they have a lot of health concerns as we move forward. So we thought BPA is a great molecule to go after. And the best thing is that there is an aptamer for it already selected. So we wanted to check if our membranes were able to remove BPA, and we start with a concentration of 200 nanomolar. And here you can observe how we are able to remove this whole area of contaminated water, and all the BPA, we're able to take it down to the EPA intake limit. Furthermore, we wanted to check if it actually translated to lake water. So we did it in lake water, and we were really excited to see that the same trend is followed, and we are able to remove BPA from water. Furthermore, remember we were talking about it being denatured so that it can be used over and over again. We decided to do certain washes with hot water to see if this membrane can be used and used again. We are able to see as we go forward with the washes that the same trend happens. We're able to remove a lot of BPA through it. So with this, we have proved that we are able to remove small molecules using Aptamer-Functionalized membranes. So now what I'm trying to do is to optimize this method to make sure that we're able to remove the most amount of small molecules for the amount of aptamer that we attach to. This is really cool, and I'm really excited to see how we can use membranes using these molecular recognition systems. If you have any questions, please let me know, and I'll be happy to answer them. Thank you so much. See you later.